Okay, so we can start. Yeah, so as it was mentioned, well, first of all, again, thanks for the invitation to give a talk here. And as it was mentioned, I got recently an ERC advanced grant, and the title was of the grant is Certification of Quantum Technologies. And certification is a concept that we are very interested in my group. And I will tell you about some results in this direction that we got recently. Okay. So in general terms, the certification problem is rather easy to understand. So you have and it somehow connects to the previous talk to the previous talk by Ignacio. So you have now systems. They can be computers, simulators, but I mean you can also think of cryptographic devices, and sometimes they are complex. They use quantum phenomena, and you want to extract relevant information about them. And what happens is that their exact characterization is very hard. So somehow you have to say relevant things about complex quantum systems with your pure classical computational devices. Okay, so this is what we want to know. We want to understand what we can say about these complex quantum systems. So in a way, this is a standard estimation problem. So you have this quantum system and you want to estimate properties about this system. So for instance, a very paradigmatic example is the one in which you want to certify that this system is quantum. For instance, you want to certify that the particles are entangled. So what are the challenges here? Well, the first challenge is that, as it was mentioned before, the number of parameters that you need to describe a quantum state of a quantum system is exponential with the size of the system. Okay, so this means that, okay, full reconstruction of the system is difficult. Okay, you require to measure an exponential number of parameters. And this is the first problem, which is, I would say, it's a problem in collecting data. And the second problem is that even if you had, let's say, a full description of your system, then, I don't know, if you want to answer whether the state is entangled, well, you have to solve often an optimization problem that again involves an exponential number of parameters. So it's difficult to solve this problem. So this makes things difficult. So I would say that we are forced to solve these questions with restricted data. Okay, usually we don't have a full reconstruction of the quantum state. Although I will be working in the two regimes. Okay, sometimes I will assume that I have the full description of the quantum state, sometimes I won't. And I also want to spend some time saying a few things about how I see estimation. Okay, so what is an estimation problem? So usually you have you want to say things about devices in your system. Okay, so this is a very minimalistic description of something that can happen in the lab. So in the lab, it may happen that you prepare some given systems and you make them evolve, and then you make some measurements. Okay, so before we had an example that Ignacio was discussing was you have a state that is easy to prepare. You prepare a single state, then you make an evolution, and then you make an observable. Okay, and here, for instance, I'm thinking of a many-body of a system made of different subsystems of particles. So what you have, you can make local measurements on these different particles. Okay, you can make different local measurements and get different results. So when you make these experiments, the estimation experiment, what you see in the lab are just probabilities. Okay, so you see the probabilities of, say, observing result R1 here and observing result R2 here. When you measure M1 here and M2 here, and you prepare the state P. Okay, this is what you see. And then you make a modeling of your experiment. So you assume that probably what you prepare here was a given state, or you were making some given measurements here. Say if you have a notion of locality, you may think that there is a tensor product here for the different measurements. Okay, this is your theoretical description of what's going on in the lab. This is what you see in the lab. Okay, so the measurement statistics. Now, what is, for instance, if you are interested in describing the state, okay, well, then usually, okay, let's assume there is no devolution. You assume that it's trivial, is the identity. And then you assume that you perfectly know these measurements. And then since you have access to the statistics and you know the measurements, the only unknown is the state. So you somehow invert this equation and you get the state, okay? sometimes you are interested in knowing the evolution of a system. So you prepare different states, you make different measurements, you know all these objects here, you know the state and the measurements, you assume that you know them. This is what you see. So again, you invert this equation and you estimate the evolution. Or sometimes you are interested in estimating a measurement. So you know the state, the evolution. Again, this is what you see, and you can infer the measurements you're applying to the system. Okay, so now see, I wrote twice problem, but there should be one. Okay, apart from this typo, what I want to say here is that, well, basically you have these different problems, no? State estimation, channel estimation, measurement estimation. And basically what you do, as I was telling you, is that you assume that some of the ingredients in the previous equation for the probabilities are known, and then you get the missing ingredient. Okay, so for state estimation, you assume that the original channel is identity, measurements are known, and the prepared state is then obtained from the statistics. I'm happy with this. The only thing I want to stress here is that what you're assuming is that some of the ingredients are perfectly known. This is why you can invert and obtain the missing ingredient perfectly from the statistics. Okay, and well, in some cases this might be a strong assumption. Okay, so to invert this equation, you need to make assumptions about the objects that you have to the right at the right hand side of the equation, because remember, this is what the only thing you see in the lab, and this might be questionable in some cases. Okay, and this is why okay, for instance, okay, this is a very old very old picture of an experiment. As you can see, I'm a theorist, but I think in some cases you may wonder whether this is for instance, if you say that this is a qubit system, well, this might be questionable, and I think in general it's hard to assign a given Hilbert space to a complex quantum setup. Sometimes we do it, and sometimes I will do it in my talk, but I think it might be questionable in some cases. Okay, this is why in some cases we are interested in making claims about what's going on in the experiment only from the measurement statistics, and we call this device-independent estimation. So you don't make any assumption about the Hilbert space or the objects that are here, here, and here, and you want to say interesting things about these unknown objects only from the measurement statistics. Okay, so this is what we call device-independent estimation, and sometimes we are interested in making device-independent estimation, which I think is an interesting scenario for the certification of quantum systems. Okay, but this is one problem, an estimation problem. The second problem is also related to what Ignacio was discussing before. So we will have devices that we will use to solve optimization problems, to simulate physical of systems of relevance. And I don't know, I will focus here in a very paradigmatic example, which is you use a simulator or an annealer to find the ground state of a system and the corresponding energy. Okay, so what you know is that, well, this problem is usually hard because there are many local minima. So, well, you never know whether you have reached the actual ground state. So what you know is that, but of course, what you know is that your system has provided you an upper bound to the ground state energy, maybe the ground state energy, but possibly not. So it has provided you, it has been trapped on a local minima, and a local minimum, and then it gives you an upper bound to the ground state energy. Okay, so any physical realization by definition gives you an upper bound to the minimum, which is the ground state energy you are looking for. Okay, so we would like to know whether this upper bound is good, okay, or whether it's good enough. And we want to certify somehow, have an estimation about the quality of this upper bound. Okay, so there are several approaches for that. I mean, of course, if you want to benchmark a quantum annealer or simulator, well, for sure, what you have to do is you have to compare the value you get with what you can do with classical techniques. Okay. So here I'm interested in a possible regime in which your quantum value is better than any classical value. Okay, by this I mean any value that you can get with a classical computer. Now, okay, this is good. It's a good sign for you because you are beating any classical method. Can you say about the anything more about the quality of this output? Okay, so this is what I want to know and what I will discuss in my talk as well. Okay, so the problem with these questions is that they are hard. Okay, so what do you do when there are complex optimization problems. So what do you do usually when you have to deal with a complex optimization problem? So there is a strategy, which is you relax, okay? You take a relaxation and you make it easier. And hopefully easy enough for you to apply some classical techniques. So what is the way to relax that I'm going to consider in my talk? Well, it's going to be the following. So I'm going to, during my talk, there is going to be a set of interests, which is, say, the set of separable states or whatever. You will see the different examples. But the important thing is that this set of interests is hard to characterize. Okay, so what I will do then, I will define outer approximations to the set of interests that have an efficient characterization, possibly numerical. Okay, so this is what it's happening geometrically. You have your set of interests that you want to characterize. And then this is hard. Then I will define outer approximations to the set of interests, different hierarchies of outer approximations. And hopefully it's even nice if you can prove that there is some sort of convergence. So these outer approximations get better and better to the set of interests. And hopefully I want to find these outer approximations, to design these outer approximations in such a way that they can be characterized in an efficient way. Okay, so this is the main idea of my talk. And I think what I want to sell you, the idea I want to give you is that this is a promising approach for the certification of quantum devices. Okay, so what is the problem I introduced? The first problem I introduced, it was an entanglement problem. Okay, so you have a system, you want to know whether it's entangled. So how should I see this problem in the previous picture? Okay, I have the set of separable states that usually is hard to characterize, and I want to give these outer approximations. So once I have these outer approximations, what I will do, if you give me a state, so I want to know whether this state belongs to the set of separable states or not. So let's assume it's entangled. So what I will do, instead of checking whether the set is in the separable set, I will check whether the state is in one of these outer approximations. Okay. And if at some point I find a good enough outer approximation that proves that the state is outside this outer approximation, then I can certify that the state for sure is not separable and it's entangled. Okay. Good. So now I will tell you about two results that we somehow got in this direction. Okay. So the first one is a paper that appeared last year together with Miguel Navas-Cres and Suki. He was a postdoc in Miguel's group. And here, what we wanted to do was to find to introduce an approach to quantum certification. I mean, I'm going to tell you about entanglement and Bell non-locality, but actually it's an approach that is more general and you can apply somehow to many problems in certification. Okay, and we call this approach connector tensor networks, and it's inspired by a renormalization idea. Okay, here the method assumes that the state is available. Okay, I think it's interesting to study how to relax this assumption. We didn't do it in the paper, but okay, I'm assuming that the state is available to start with. So what is the intuition? I will explain this with entanglement. Okay, so you're given a state and you want to know whether the state is entangled. So in particular, you want to know whether it cannot be written in this form. Okay, so if the state can be written in this form, it's separable. So what I do, I will let's consider for a while that I have a map that maps states from two particles into one particle. Okay, so it's a Gauss-Grain map because it maps two particles into one, and such that this map, it doesn't need to be completely positive, it doesn't need to be physical, but it maps product states into physical states. Okay, you see here I'm demanding that my map takes a product state and gives something positive. Okay, so well, this is before I was telling you, I mean, the simplest consideration is when you have say two particles into one, but in general, okay, I leave these dimensions arbitrary. So, but of course, if I take the output dimension d0 smaller than the input dimension, which is the input square, then this map contracts the space. So you can see there's a Gauss-graining. Okay. So in particular, you can see this, if d0, the output is equal to the input, this is you map two particles into one. Okay, so you have your state of n particles and it's mapped into a state of n-1 particle. Now, what happens if you apply this map to a separable state? Well, remember that this map has the property that any product state goes into a state. So this means that if I'm applying here the map to the last two particles, you see here, okay, I can put this map into my description. Then I'm mapping these two particles, and this is a product state. So this will become positive, and this will be a positive state. Okay, so what I do, I start applying these maps to different set of particles. Then I coarse-grain my description. But the interesting thing is that the property I'm interested in, the set of separable states, does not change. So I'm not moving states from the separable state outside the state, and actually I'm not even mapping these states into something non-physical. Okay, they remain positive, and actually they remain even separable with this map. So what I can do, I coarse-grain my description until I have a size where I have a criteria to check entanglement, or I could even check positivity. Okay, if I see that the resulting state is not a state, or the resulting operator is not a state, or it's entangled, then for sure the initial state I started with is entangled. Okay, and just for those who know entanglement witness, well, an entanglement witness is an example of those maps. Okay, these maps, we call them connectors. Okay, so an entanglement witness is a trivial example in which the output dimension is just, well, it's just a scalar, and we demand for an entanglement witness that is positive when acting on product states. Okay, so this is one element, and we were interested in applying this construction to tensor network states. Okay, or, well, let me just start again. So a nice thing is that you can understand this construction in a pictorial way using tensor concepts from tensor networks and tensor network notation. Okay, so in tensor networks, you represent states through tensors, and you can also make operations with these tensors. So basically what you do when you, okay, so basically the edges that represent indices. If they are open, these indices are not contracted. If they are linked, these indices are contracted. Okay, so for instance, here, this is a vector because there is an open index. This is a matrix. Okay, and here, for instance, C, it's another 3 tensor index. Okay, and D is a matrix multiplication because this index is contracted. Okay, so I guess people here know much better than me about, many people know much better than me about tensor networks, but it was a useful language for us. And actually this language is used a lot in condensed matter theory. So there is MPS that have a tensor network representation. There are metas that have another tensor network representation. But with tensor networks, you can represent other objects. So for people who work with non-locality in the device-independent scenario, we also work with correlations, and you can also represent these correlations as a tensor network. Okay, where the indices now label the output and the input of your Bell experiment. Okay, so what is the idea? You have the object, and here I'm not assuming any structure. So this is my object made of n qubits or n devices in the device-independent scenario. And I start applying these coarse-grain methods. Okay, so you see I coarse-grain. And at the very end, I apply a criterion for entanglement. And this criterion, you can also see it as a connector. Okay, if it's an entanglement witness, as I was telling you, this is a connector. So you start doing this, and at the very end, you check whether this is a positive or negative, and this tells you about the entanglement of the initial state. Okay, so this is the idea of the method. And the good thing is that in many cases, the characterization of these connectors is efficient. You can use techniques from convex optimization theory. So basically, a possible way you can do is you start with some random values for these connectors. Then you fix all of them, and then you optimize over 1, trying to minimize the value of this quantity at the very end, okay? Because you want to minimize and make it negative. And then you run this in a seesaw operator, and then you fix it, and then you fix all by 2, and then you minimize. And then you fix, and you, okay, you can also apply a gradient descent, okay? What I'm saying is that in many cases, you have an efficient characterization of these objects, and then you can minimize and hopefully find prove that this minimum is, or find a good value for this contraction, and then prove that the state is entangled. Okay, so this is the idea of the method. So for instance, let's imagine that you are interested in a Bell experiment. So in a Bell experiment, you are making measurements on different particles, and the choice of the measurement is labeled by X, and the output is labeled by A. So you see the statistics. Bell experiment is a device-independent experiment, so you only work with the statistics. Okay, this is what I said before, and you want to know whether these statistics violates a Bell inequality or not. Okay, this is hard in general, okay? Because basically what you want to know is whether these statistics can be written as a mixture of deterministic points, local deterministic points, and this is hard. I mean, you can, in principle, it's linear programming, but the problem is that the number of extremal points grows exponentially with the size of the system, okay? So already, say, for 10 particles with 2 measurements of 2 outputs, you cannot solve this problem with full generality. Okay, so the nice thing is that these connectors, the objects that map, okay, what is a connector here? The connector here is something that maps local correlations into a probability. Okay, I mean, in the previous example I gave you, you were mapping product state into a state. Here you have to map local correlations into a probability. Okay, and this can be characterized. I'm not going to spend time on this now, but it can be characterized using linear programming. And the good thing is that now, as compared to the previous case, you want to simply characterize those connectors acting, say, on 2 systems into 1 or 3 systems into 2. Okay, so I mean the size of the connector does not grow with the system. So you can solve this with linear programming. Okay, so I mean, I'm not going to explain this. I can give you more details later if you're interested, but everything is linear in this, so you can use linear programming to find connectors. And well, you can characterize them using linear programming. So when you have to optimize over connectors, you can use linear programming. So this is efficient. Okay, so for instance, we made some numerical experiments, and since these connectors have a sort of renormalization inspiration, you can see that they are especially powerful if you have objects that you can efficiently describe with tensor networks. Okay, so for instance, what we did, we took a GXZ state for which we have an efficient tensor network representation, and we made measurements on sigma X and sigma Z on this GXZ state. So this gave us a probability distribution that also has an efficient tensor network representation. And then we were checking whether this point is non-local, okay? And we could prove the non-locality of this point, okay, up to systems of 100 particles, okay? I mean, remember what I was telling you, that at a brute force approach, you can go up to 10. Here, we could easily go up to 100 particles, okay? So this shows that approach, I mean, well, it depends on your data. So, but I was telling you, you have an efficient description in terms of tensor networks, then you can run this system, and sometimes you can get certify the non-locality of the statistics you are dealing with. And we could do something similar for entanglement. As you know, if you know about entanglement, you know that usually what you do for statistics for correlations for local correlations with linear programming in separability, you have to use semi-definite programming. It's another technique from convex optimization theory. So perhaps not surprisingly, the connectors for separable states can be characterized using semi-definite programming, and we did something similar. So we took 6-qubit PP6 states, and we also consider 60-qubit that have an efficient matrix product density operator decomposition, and we could prove the entanglement. Okay. Okay, I might say that this method is heuristic, so we could see that it works well, but I have to admit that in some cases it didn't work. Okay, so we had some cases in which we were running the method and this optimization was not finding a value that was negative. Okay, but at least it is a technique that allows you to to operate of systems of large size. And I'm telling you briefly about 2 applications, non-locality and entanglement, but we could also apply to other relevant sets of resources. Okay, so we also apply to steering, or we could also apply to estimating the dimension of your system, something called dimension witness. Okay, because basically you always have to deal with the characterization of these connectors, and usually these connectors can be characterized with convex optimization tools. Okay, so this was the first problem I wanted to discuss. The second one is here is the entanglement marginal problem. And this is together again with Miguel Navasquez from ICFO Vienna. I didn't mention this before. And Flavio Baccari, who is from MPQ. Okay, so this the scenario we have in mind is the following. So assume you have a system, and it's very hard for you to make a full tomography. So now I'm not assuming that you have the a full description of your state, but you can estimate a subset, the state of subsets of your system. Okay, so you can estimate reduced states of your system. And I will denote the states you can estimate by I. Okay. Okay. So you can understand here what is happening. Okay. So you have this system made of 11 particles, and you are given these marginal states. Okay, which is something that you can characterize with a non-exponential effort. And now you want to know from these states, you want to know whether the global state is entangled. Okay, well, first of all, I mean, this problem is especially meaningful if the states you are given are separable. Okay, so of course, the first thing you have to try if you are given these marginals is to check whether the marginals are entangled. Okay, so because if the marginals are entangled, for sure the global state is entangled. Okay, so I'm not interested in this problem. Or it could be that they are entangled, but you cannot see it. Okay, so well, then you are given these marginals, and you want to know whether the global state is entangled. And of course, this problem is, for this problem to be meaningful, these marginals cannot be arbitrary. They have to satisfy some compatibility conditions. Okay, so for instance, if you look at here, row 1 and row 2, they overlap on this qubit. So this means that the trace of row 1 over these two particles, which gives the state here, is the same as the trace of row 2 over these 4 particles. Okay, because this row 1 and row 2 coincide on this qubit. So the state of this qubit should be the same if independently of whether you compute it from row 1 or row 2. Okay, so these conditions are called compatibility conditions. Okay, so what I demand is that if I have overlapping marginals, they have to be equal in the overlapping region. Okay, so this is the input to my problem. I'm given a set of marginals that satisfy these compatibility conditions, and I want to know whether these marginals are compatible with an entangled state or with a separable, actually whether they are compatible with a separable state. Because if they are not, then I know that the state is entangled. Okay, so again, in the previous picture, what I want to know is, okay, this is the set, okay, I'm saying separable marginals, but what I mean is the set of marginals that are compatible with a separable state, okay? And then I want to design outer approximations to this set, and again, conclude if a state is not in the outer approximation, for sure it is not in the separable set. Okay, so to understand what we did, it's also useful to remind the classical marginal problem. Okay, so what is the classical marginal problem? It's the same I'm telling you before, but now you don't discuss about separability or entanglement, but you simply discuss about whether there exists a probability distribution compatible with some marginals. Okay, so the problem is similar. So you have a system made of n particles, and I define probabilities for subset of the particles. And now I ask whether these probabilities are compatible with a big probability for all the particles. Okay, so this is the classical marginal problem. Okay, so I'm giving measures or probability distributions for a subset of particles, and then I wonder whether this is compatible with a global probability distribution. And this is not an easy problem. Okay, so I'm not sure if it, well, I don't remember now the complexity class, but it's complex. And again, the problem is meaningful only if also these probabilities have to satisfy this compatibility condition. Okay, so if I look at the marginal of two probabilities that overlap, okay, whose domain overlap, then of course the probabilities have to define the same probability at the overlapping region. Okay, this is what I'm asking here. Okay, as I did before for states. And these compatibility conditions, the local compatibility conditions, are known not to be sufficient for the classical case. Okay, so I can give you distributions that satisfy these compatibility conditions. They look that they could be the marginals of a big probability, but it's not the case. Okay, so what we know, and this is something that will be useful in what follows, is that if the entanglement marginal has a solution, okay, which means that I have a quantum state for the big system that is separable, that is compatible with my reduced state, okay, so this, it means that I can define a state for my big system, which is separable, okay, then I can trace out the particles and take all the marginals that was given, okay, and what appears here is some probabilities that satisfy the classical marginal problem. Okay, so I hope it is clear. What I'm saying is that if I have a separable state compatible with the given marginals, it means that my quantum state can be written in this form for the global system. Then I can compute the reduced states by tracing out here the parties. And the classical probabilities that appear here in the separable decomposition have a solution in the marginal problem, okay? Because I can go back in terms of probabilities. Okay, so what is the method we found? It's inspired by hierarchies of methods that exist for entanglement, okay? So let's assume that this separable global state exists, okay? So this is a state for the n qubits, and it's separable, okay? Which gives me the marginals I'm looking for. Okay, what I can do if I have this decomposition, what I can always do, I can construct a larger state in which I copy the product states in each system. Okay, so you see here, this is the marginal, and what I do, I take copies of my product state for each system, L copies. Okay, I'm not saying that I can do this with the marginals, but what I know is that if I had this description, I could do this. Okay, so this is telling me that if this global state is separable, I can define these states, and these states have satisfy different properties. So if I trace L-1 system, I'm back in the previous description. So I'm getting the states I was given. You can also see that these states are PPT according to some bipartitions. Okay, they are positive under partial transposition. For those who don't know about PPT, it says that they satisfy a given condition coming from this form, from this structure. Okay, they have a series of constraints here. And the nice thing is that these constraints I can easily check using something called semi-definite programming. Okay, and if the state is compatible with a global separable state, the marginals are compatible with a global separable state, I can always run this argument for any L. Okay, so I can always do this, construct these extensions for any size L, and these extensions will satisfy these properties. Okay, so what I need to do then is, if you give me the marginals, I ask whether these extensions exist satisfying the properties. If they don't, then the marginals are not compatible with a separable state. Okay, and this I can check with semi-definite programming. Because if the marginals were compatible with a separable state, I could write this, I could take this, and I could construct these states satisfying these properties. If this has no solution, this means that this is not true, hence the state is entangled. Okay, and again, this defines different outer approximations for different values of L. I can start with L equal 2, L equal 3, L equal 4. This means that the state of this is increasing, okay, but still the increase is, the states are symmetric, so it doesn't grow very dramatically with L. And then I can run these tests. This is a hierarchy of tests, and I can answer whether the state is entangled or not. So again, these are outer approximations to my set of interest. The question is whether this eventually converges. Okay, so what we could prove based using results by Miguel, so actually Miguel proved this using his previous results, was that the hierarchy tends to the, it doesn't tend to, so if you pass all tests in this construction that I was giving you, you cannot prove, you cannot solve the marginal problem, but you tend to states that can be written with probabilities that satisfy the classical marginal problem. Okay, so it's a bit, I'm not sure if I have another slide. No. Okay, I hope you will understand what I'm saying. Okay, but in the example. But what I'm saying is that what we can prove in this case is that if you pass all the steps in the hierarchy, you tend to a set that is strictly larger than the separable states, and it's the set of marginals that can be written with probabilities that satisfy the classical marginal problem. Okay, maybe this was a bit technical. Let me try to explain it with an example. Okay, let me take states in a line. And you are given only the marginals of two neighboring sides. Okay, you're given 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. Okay, this is the input to your problem. Okay, you can run the test. Okay, so every test is polynomial in n. Now, what does this hierarchy of tests tend to? So it tends to the set of marginals that are separable and whose probability satisfies the marginal problem. Satisfies, sorry, the local compatibility conditions. Okay, sorry, I made a mistake. So the hierarchy tends to the probabilities that also satisfy the local compatibility problems. So when I run my method here, I have this set to states that are separable and whose probabilities in the separable decomposition satisfy the local marginal problem. What happens is that the classical marginal problem in this case has always a solution. Okay, so if I give you some probabilities such that probability in 2 is the same coming from 1, 2, or 2, 3, and the probability in 3 is the same coming from 2, 3, or 3, 4, then there exists a global probability distribution for the whole system. And this follows from this simple identity, okay? So you can see here that I can construct a probability distribution for the whole system only from the marginals if the reduced marginals are well defined. So for instance, assume that the state was of 3 particles. If you sum over 3, this disappears. This becomes P of x2. Px2 you divide with the denominator, and you are back with the marginal for 1 and 2. Okay. I think I forgot here the px1. Okay. No, okay, it's okay. Yeah. Yeah, it's okay. It's okay like it is. Sorry. Okay. So these methods that we applied can also be also considered for infinite systems. Okay. Well, of course, infinite systems, you took marginals. I mean, if you don't have symmetries, the set of marginals you have is infinite. So the problem doesn't make sense. So we are considering infinite system with symmetries. And then you can run these arguments, okay? And for instance, the simplest example is a case where you have a chain with translational invariance, okay? So then the compatibility condition tells you that you look at the state of, say, system 2 to n, okay? This is the same as the reduced state of system 1 to n minus 1, okay? So you can apply this local relational invariance for your compatibility of the marginals. Okay, and then we can use a similar structure I'm not going to tell you about, but we can also solve this problem. And for instance, for the case of translation invariance, we can, the hierarchy converges. Okay, this is what I'm telling you is that you have a system of arbitrary size and you give me the marginals of contiguous sides in a chain. I can run this method and I can, if I'm lucky, at a given point in my hierarchy, I will be able to tell you that the state is, the marginals are not compatible with a separable state. Okay, so this is the second that I wanted to tell you about the entanglement, and the third last problem I want to discuss is the one about the ground state energy. Okay, so here you have something that gives you a ground state energy. It can be a classical quantum system. We want to know how good this value is, and this is something we did again with Flavio, with Christian Gogolin, who was at Covestro, who was at ICFO, but now he's working for Covestro, and Peter, who was at ICFO and who passed away, unfortunately, some years ago. So here we're interested in an application of quantum systems to solve classical optimization problems that you write using a classical spin system. Okay, so you can encode the solution to some relevant optimization problem in the ground state energy of some classical spin systems, and you write it in this form. And the solution to this problem is given by the ground state energy of this system. And then you try your best method to find the ground state energy. And as I was telling you before, you will get an upper bound to the ground state energy. So what is the problem you want to solve? You want to solve this minimization. And you can see that basically this is a minimization of some variables, and these variables are classical spins. So they satisfy this constraint. Okay, so the square of your value is equal to 1 that you can write in this form. Okay, this is a polynomial optimization problem. Okay, because you want to minimize over these assignments of spins. These j and h are given, depend on your problem, and you satisfy this polynomial constraint. And there are results for polynomial optimization problems. Okay, so basically a polynomial optimization problem is any problem in which you want to minimize the value of a polynomial subject to some polynomial constraints that I write. These are polynomials over the same variables. Okay, so this is, for instance, an example, or my previous ground state problem, it was another example. So how can you deal with this? So what you do, the polynomial constraints define a set of feasible points. So these are the points that satisfy your constraints, okay, that I represent by this set. I put it in this very simple form. It might be highly non-trivial, okay, but just, and then your polynomial is a given function of your unknowns, okay? And then you want to find the minimum of this function, which is here. Well, it depends on how this goes. But for the points I'm showing here is here, but you want to find it over the feasible points, which are in this set, okay? So what is the solution I'm looking for in this particular case is here, okay? So this is the minimum over my relevant set. And many of these problems are hard, and basically they are hard because it's very hard to characterize this set, okay? So as it happened before, it's very hard to characterize this set, and then it's very hard to identify the point within the set that minimizes the function. So there are techniques found by several people, for instance, by Lasser and Parrillo, that they follow the same logic as I was telling you before. Okay, so you construct outer approximations to the set of interest. And these outer approximations are easier to characterize. In particular, in these methods, you can run semi-definite programming to characterize these outer approximations. So instead of solving the original problem, you minimize this function over these outer approximations. So, and the nice thing is that since you are optimizing over a larger set, the solution you will get either is the minimum or something smaller than the minimum. Okay, so for instance, in this instance, if I minimize over gamma 1, I will get this solution, okay? Because this is the minimum of my polynomial over the points that are within gamma 1. If I optimize over gamma 2, I will also get this solution, okay? But if I optimize at a given gamma, at some point, I will get the solution I'm looking for. And what happens is that for these hierarchies, they converge to the solution only asymptotically. Okay, so at the very end, you have to run and you have to deal with an infinite problem, but you know that they give a non-tonically improving set of lower bounds to the search solution. And the good thing is that it gives you lower bounds, okay, because you optimize over a larger set. So now you can take these methods and apply them to the ground state problem I was telling you before, and you will get lower bounds to the ground state energy. Okay, and this is interesting because it complements whichever method you can think of using physical systems. Okay, because a physical system by definition can only give you upper bounds. Okay, so this can give you lower bounds, and then you can define an energy range in which your solution is. So what we did, we took these methods and we introduced some improvements over some of these methods, and we applied to classical spin systems. Okay, so we ran these outer approximations using semi-definite programming, and we were getting lower bounds to the ground state energy. In this case, from the solution, and since we are dealing with a system of classical spins, from the output of our method, we could also easily get an upper bound. I'm not going to tell you about how we did it, but it's very simple. Okay, so running this semi-definite programming, we could get a lower bound and an upper bound. And once you have a method that gives you a lower bound and an upper bound, there are techniques to combine them, and then using something called branch and bound, and then close the gap between these two solutions. And this is what we were doing. Okay, so we're getting lower bound, upper bound, and we're improving. And heuristically, we could see that in many cases the gap was closing. So actually, we were solving the problem. Okay, we know that this cannot be the case always because spin type problems are NP hard. But okay, if the gap does not close, at least at a given step, you will stop and you will have a provable energy range in which the solution lies. Okay, so in this sense, it's better than an upper bound or than a single upper bound, because for a single upper bound, you have no idea about how far you are from the energy. Here, with this method, you can have always control about where the energy is. Okay, and actually we could see that in many cases the gap was closing. Okay, this method scalability is not as good as Monte Carlo. Okay, so for instance, for the problems we were considering, we were using some tricks because the problems we were considering had local interactions, then they were sparse. And well, Flavio can tell you much more about this, but he was, I think, dealing with problems of say 1,000 spins. Okay, so Monte Carlo can go solve larger problems, but again, Monte Carlo does not give you this information. Okay, so does not give you an upper bound and a lower bound at the same time, to my knowledge. And then we took this method, and we were also comparing this to a D-Wave machine. A D-Wave machine, one of the applications to solve these spin problems. And well, I mean, we were running, and sometimes we could see that the D-Wave machine was getting the same as us. Sometimes the D-Wave machine was stuck in a local minimum. So then we were asking the D-Wave machine to recompute the value. And eventually the D-Wave machine was getting the same as our method, but sometimes it was not the case. Okay, so we could see how this method could be used together with a quantum annealer just to benchmark the quantum annealer. Okay, with this I come to the conclusions. So I think, and I hope many people here appreciate that the certification of quantum properties of many-body system is a fundamental problem. I mean, for science and also for the development of these quantum information technologies. And I believe that the relaxations of these problems are promising in this sense, okay? Because since you approximate from the outside, you certify, okay? So, and for that, you have to see how to give outer approximations to the relevant sets of interest. And then I was telling you examples of how to do that for entanglement non-locality, but as I was telling you, this renormalization approach can be used for other properties. And then I was also telling you how the same approach of relaxing can be used to obtain lower bounds to spin systems that are analyzed using quantum annealers. Okay, but I think in general, yes, and this is the problem of quantum certification. Okay, so how can we certify quantum properties of relevance of complex quantum systems with our limited classical processing capabilities? Thank you very much for your attention.
Well, thank you.